welcome to our next lesson. Last time we started discussing random variables and probability distributions, and then of course the expected value calculations that you could do with those. Today we're going to start a series of lessons into specific types of probability distributions, and we're going to start with probably one of the most useful ones, one that we've talked about a couple of times in passing in some of our previous videos, and that's the binomial probability distribution. Now, probability distributions, what we're going to start doing is we're going to start defining a set of criteria that define a particular distribution, and then once we meet that set of criteria, then we'll derive the formulas that we can use to be able to estimate the functional shape of the probability distribution itself, or that probability mass function. So, as we were saying, the binomial distribution is based off of a binomial experiment. Our definition of a binomial experiment has a couple of criteria here. The first one is that the experiment consists of n number of trials that are fixed in advance. All right, so basically we're going to look at something 10 times, or we're going to look at it 15 times. We're going to know it ahead of time. We're not going to say we're going to repeat this experiment until we get a certain outcome. Those are not what a binomial experiment is. So these are, if you see the word until, it's not a binomial experiment. All right, the second one criteria is that each trial result, okay, is one of two outcomes. That should be and is. Okay. Either, typically a true or false, or a yes or no, or more often, more powerfully, is, an event and then its complement. So I use the example of blue and not blue. So, we could be looking, and we've talked about this in some of the previous examples, how we can cluster or condense a problem into a criteria that I'm looking for and then everything else, and that's probably the more powerful of the option. Okay, all the trials are independent, so the outcome of one trial does not affect the outcome of a later trial in the set. Okay, and then finally, that the probability of success is constant from one trial to the next. All right, so this basically implies that we are doing a with replacement scenario. Right, so if I'm pulling cards out of a deck, I have to put them back in because I've got to maintain a constant probability on this. So those are the four major assumptions that go into a binomial experiment. So if you don't meet all four of these, this is not, your experiment is not a binomial experiment, and then the rules that we're going to show you here do not apply. Okay. All right, so I'll give you kind of a couple of simple examples here. We can toss a coin 10 times. We can let success be heads, a failure be considered a tail. And we're going to repeat this process, like I said, 10 times, and what's the probability that we get at least 5 heads? That would be a type of an experiment, assuming that, of course, that the probability is a half, or it doesn't even have to be a half. As long as it's consistent. It could be an unfair coin, but as long as the probability is consistent, this one would meet the criteria for that. Okay, the next one would be, selecting a card from a deck 20 times with replacement. Again, the with replacement issue is a major consideration because we have to maintain that constant probability. And again, we can define, in the context of a previous example, that, we'll define our experiment as a success if we pull an ace and a failure if we don't pull an ace. And so we could say, what's the probability that we get, no more than 2 aces on this. All of these will be able to be solved by a binomial experiment. Okay, now, the rule of thumb for binomials, and what makes binomial experiments so powerful, is that we can treat without replacement experiments as binomial experiments so long as the sample size is a small number, small percentage of the population. And a kind of a rule of thumb, we say if our sample is less than 5% of the population, then what happens is we find that this probability change is minimal. It's not a huge difference in probability from one case to the next without replacement. Okay, now, so if I have, 100,000, people that I'm polling for something, and I'm asking them a question, a yes or no question, 5% of that number, is a small value compared to, if I were asking 20 and looking at that, that's kind of the issue that we're looking at. It's all about keeping this probability constant from one trial to the next. So that's the setup for our binomial experiment. All right, so let's talk about then our binomial random variable, because that's where we want to go, and that's what we've been doing the last couple of videos, is trying to define this. So what we're going to do is the binomial random variable is we're going to use the letter x to represent this, and it's going to be the number of successes in n trials Okay, so we're measuring success. Okay, so we're going to define S as success and F as failure, whatever the criteria is. Okay, and so let's just write one of these out, that we're going to consider the number of successes in 4 trials with the probability of success being some value of P, this script P that we have here. All right, so what I've done is this problem's small enough that we can actually write out all of the cases and all the scenarios. So that's what I've done. And we kind of did this in one of the previous exercises, but now I'm going to kind of elaborate a little bit more on the notation and those kind of things. So what we do, because it's a random variable, we consider all of the values, possible values of x. And again, x is the success, number of successes in n trials. So if we're doing 4 trials, then my possible answers for x are 0, 1, 2, 3, and 4. There are no other options. So if x is 0, there are no successes. That's the all fail case. And so we can write that as the probability of x equals 0, and that's going to be 1 minus p raised to the 4th power. And so 1 minus p, p is the probability of success, 1 minus p is the probability of failure. So that's why that piece is here. Okay, we go to x1, and so now we get into the scenarios where I have 1 success in all of these. And so there's a success in the first, a success in the second, success in the third, success in the fourth. That's all that can happen. And so my probability of x equals 1 then is 4 times p, okay, multiplied by 1 minus p cubed. Okay, so again, I have p raised to the 1 power and then 1 minus p raised to 3, because there's 1 success and there are 3 failures in this string or in this pattern as we start to look at it. X equals 2, we're looking at 2 successes, and so I end up with 6 patterns: success SSFF, SFSF, SFFS, and so forth and so on. And so I have 3 successes in the first one, 3 failures in the first one, and then the arrangement of 2 successes out of the failure, and so forth. You can kind of see those. So for probability of x equals 2, then there are 6 scenarios. Okay, so now I have 2 successes, I have 2 failures, and then there are 6 of them, because there are 6 ways that arrangement can matter. Okay, now if you kind of look at this, we're kind of looking at setting ourselves up for some sort of combination calculation on here. All right, because we're looking at the number of ways that I can pull this pattern if order doesn't matter. Okay, the x equals 3 then is the 3 cases. Okay, and so there are 4 of those that show up, and then I have 3 successes, so p cubed, 1 minus p, and so that's raised to the 1 pattern. Okay, and then x equals 4 is all 4 success. There's only one way that happens, and that's a p to the 4th. Now, if you look at this, you start to see kind of a pattern developing on here, and I'm going to show you kind of what the pattern is, that I can do a 1 minus p here raised to the 0 power, and then on this first one, we could say that that's a p raised to the 0 power. Okay, and if you look, there's a direct correlation between the exponents on this term, that 0 is 0, 1 is 1, 2 is 2, and so forth and so on. And then what happens on the other one is then that this guy becomes kind of an n minus x calculation, that, that 4 minus 0, is this value, and so forth and so on. And you can start to kind of see how these chains start to get built. And so there's a pattern that develops, and that's what we wanted to see, because that allows me to define a basic equation for calculating these probabilities. So the definition that's written in the book is a binomial experiment with n trials and the probability of success equal to some value of p. Okay, and so what I'm going to do is I'm going to write my notation as this. This basically says that the random variable x is binomially distributed with n trials and a probability of success of a certain value p. Okay, the PMF then is given by this, again, writing it a little bit differently. X is some value, n and p. What you'll see in the examples that we'll start to write is, we'll start to write it this way. It's kind of a shorthand notation, that this lowercase b represents a binomial. There's my value I'm looking for, in trials, probability of success. And this whole equation, the general form of all of these that we wrote up here, looks something like this. And again, you've seen this before. We talked about this one in one of our previous videos, okay? But it's the combination of the number of ways I can pull x successes out of n trials times the probability of success raised to the x power times 1 minus the probability raised to the n minus x power. So here's my successes, here are my failures, and then this is the number of ways that I put them all together. Okay, so it's just a counting exercise at this point, and then x has possible values of 0 all the way up to n. All right, so that's our experiment, and that's pretty cool, okay? Now, there is a CDF that is given, okay, a cumulative distribution function, and sometimes, again, this allows us to solve the question of random variable x less than or equal to some value. And again, we've talked about how to accumulate these cumulatives, okay? And we did that in one of the videos, one or two lessons back, when we were talking about discrete random variables. And this can be pretty handy for tallying things with large numbers, okay? And again, we'll show you an experiment, an example problem with that as well. But we're looking at, again, the summation of from y equal to 0 up to my value I'm looking for of x, of the binomial of that value of y given n and p. Okay, so it's the same thing. So it's just we're summing all the values less than y to tally up my value. Okay, now in our textbook, the DeVore text, and in a lot of probability and statistics books, these cumulative functions are sometimes tallied for you. All right, so I'm going to pause the video and I'm going to pull up the book for you, and then we'll be right back. Hold on. All right, so here we are. And so what I've done is I've gone in, and our particular textbook has several of the cumulatives listed here. Okay, so what I've done is I've showed just a couple of them on here. And so for specific values, each of these tables are set up for a certain number of n's, n trials, and then they list a number of probabilities of success, or p-value, if you will. And so here we have 1%, 5%, 10%, 20%, so forth and so on. So they've got a lot of the major ones on here. And then all you have to do to calculate the cumulative, that if I want the cumulative for my random variable less than or equal to, say, so we're in the 5 table, say I want the 3 or less on here, all I do is I read down to the x value, the value of the little x that I'm looking for, and then I read across to the probability that corresponds to the probability of success. So for this, if we have a 50-50 chance, say we're flipping a coin and we're flipping it 5 times, the probability of getting at least 3 of them then would be 0.812. That value right there. That's all there is to it, and that gets me the cumulative. So that's pretty cool. If I can build this value, then all of a sudden I can back out the individual discrete values. So say I wanted the probability that x is exactly 2, I could take the probability of x less than or equal to 3 minus the probability of x less than or equal to 2, and that will give me the probability of that particular outcome. It's pretty cool the way that it kind of works. Okay, and so again, the hardest part of this is making sure you get into the right table. Now again, they don't give you all of the tables. So so like our textbook has 5 and 10 and 15 and then 20 over on the other page. Okay, so if you have some other number that's not in the table, you can't use the tables, but you can derive it. And in fact, it's really easy to set this up in Excel or in MATLAB or something like that. This is kind of a possibility, but that's a pretty cool method. Right now, I will kind of mention here that, like I say, MATLAB can be pretty handy for tallying up some of these things. That I'll give you a couple of functions on here that we could do. It's bin o PDF is for the lowercase one. This will give us our value here. All right. And that becomes x, n, and p become the parameters. Or sometimes you'll see bin o CDF for the cumulative of x, n, and p become very, very handy. Okay, so if you're doing MATLAB on there, those are pretty cool. Okay, and so all you do is just basically pass in the variables, and then it will return the value of that probability for you. So those are very, very useful. So I'll mark those down on the notes for you as well. Okay. All right. So now on to our next page. All right. So let's try one. Give ourselves an example here. Okay. And what we're looking for, in this particular example, is maybe we're in some sort of quality inspection. And so I pulled a problem that is basically that we're looking at fine crystal goblets, and we're inspecting whether or not it has some sort of cosmic defect. This is affectionately called as a second run, or it has an error. Generally, you get a reduced price on these because there's a flaw or something that's not perfect. But the idea is that we're looking to see the probability of a cosmetic defects is taken as p equal to 0.1. So this is binomial because it either has a defect or it doesn't. Okay, and so what we're looking at then is maybe the first question is that we want to find the probability that there is only one failure, okay, in 6 checks. Okay, and so by failure, we're looking at a probability of 0.1. Okay, and so that's so we got to kind of be careful on our words. We're saying failure as in it has a defect, but in our random variable case on this, x is our random variable that it has a defect. Okay, which is what we're defining as a failure. So don't get tripped up on the words, and this is kind of a common tactic on quizzes or tests where they try to trip you on the words. I don't do it intentionally, but it has been known to happen on here. But so you have to basically always write this random variable down and what it actually means. And so this p, so the probability that my random variable x is equal to, some value, we can now start to do our binomial on there. All right, and so this is then the probability of a defect, okay, or what we call as a failure. It's not a failure of the experiment, so to say, but that becomes a 0.1. So be kind of mindful of some of the terminology. So we have, in this case, we have 1 success, which is a defect on here. We have 6 trials, and then we have a 0.1 rate of defects on here. So the nomenclature, the way we write this, is that this would be what I'm looking to calculate. The function that we look is that it is a binomial on 1, 6, and 0.1. We'll set that up, and then all we do is basically plug in the parameters. So we're going to pull 1 out of 6. Okay, we're going to do a 0.1 raised to the 1, so 1 defect, which is our success definition, and then 1 minus 0.1 would be no defects, or our failure definition, and 6 minus 1 is the exponent, and all that will get you 0.354. So it's a 35% chance that you'll have a probability of at least 1 failure in 6 weeks, or 6 checks. Okay, the next one is, let's look at the probability that there are at least 2. So again, keyword in this is at least. Okay, so probability of x greater than or equal to 2. So this could be values of 2, 3, 4, 5, and 6. So we're going to look at, we could do it the brute force method, where I just sum from 2 to 6 for my variable of x, in trial 0.1, and I calculate this for each value of x. Gets me 0.114. Now what we've done is I've written it out for you as I do the binomial of 2, the binomial of 3, binomial of 4, binomial of 5, binomial of 6 on pools of 6 at this probability. I could do that. Now, if you had 100,000 of these, this is not the way that you would want to solve this problem. So an alternative is to go in and do our cumulative function, where we say that the probability that x is greater than or equal to 2 is the same as 1 minus the probability of x less than or equal to 1. All right, so that's our complement definition. And so now I can do 1 minus our binomial CDF. Now again, I didn't point this out on the last page, but notice that the lowercase was a b for a regular binomial, and then the capital B indicated our CDF. Okay, that this is a cumulative function. So watch the nomenclature. So here it was a capital B, up here it was a lowercase. Okay, so be mindful of that. And then we're looking for less than or equal to 1, 6, and 0.1. And so that probability coming out of, if you had the tables, we didn't have the tables for this one, but you run it through MATLAB or you fill out the calculations for this. Okay, that 1 failure in 6 checks would be 0.886, and then that number again is 0.114. It's the exact same number regardless of the way that you go. Okay. All right, the next one then is that if we examine one by one the probability that 4 of the next 5 are not defective. Okay, so what we're looking for then is that the probability that x equals 0, okay, that there are no defects in the first 4, okay, plus the probability that there is 1 defect in the first 4, again, taken out of 4 and 0.1, and then 2 this because we're saying that 4 of the next 5. So what's happened here is we're kind of looking at setting up these strings that, like, for the first one, when there's no defects in the first 4, I've already met the criteria. I don't care what happens on the 5th one. Okay, that basically we would be doing a 1 minus p raised to the 0 power on this term. It's kind of hidden and implied there. Okay, whereas on this one, if I pull 1 out of the first 4, then I have to have another, the last one must not be defective. And so those are the 2 cases that we got to kind of work at on here. All right, so be kind of mindful. So this pattern is basically saying I'm doing, a set of, let's see, what would be success, 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 fail, and then that means that this last one has to be here. And so this could be, You know, success, success, fail, success, success, fail, success, success, and then fail, success, success, success would be all of the cases that come out of that first one, and then multiplied by the probability that in order to meet this criteria, then the last one has to be a success. All right, so that's why we kind of chain these events together, whereas this one, you know, I've already got the successes, I've met the criteria. So for x equals 0, it's just the number of ways of pulling 0 out of 4, and then the probability of x equals 1, okay, for our definition. And so when we do that, this definition becomes a binomial of 0 on 4, and this one becomes a binomial of 1 on 4 multiplied by 1 minus p, which is where that 0.9 is coming from, and that again is raised to the 1 power. And if I do our math, then we're looking at, you know, examining one by one the probability that 4 of the next 5 are not defective. Okay, now again, we get into that with replacement, without replacement. We're looking at ways to, you know, if we assume that we're doing a huge population run, that the chances of pulling one out of the set, you know, it's, like I say, it's still a binomial experiment, but don't get hung up on the without replacement or the with replacement. This one meets the criteria either way. All right, so, and again, we're looking at small numbers, and so we're going to get about 92% for that one. All right, okay, now, the last bit of this then is that once you've identified how to work with this PDF, now we can go in and we can start calculating expected value and variance and standard deviation. So we can go through and go back to our definition of expected value, where I sum up all of the x's times their probability. So, which would be this equation. This is the same as what we did before. And so I'm going to sum from x equals 0 to n of all of my x values times its corresponding probability. So this is the variable that changes. So you can see that this equation here is exactly the same as what we had here, which is our definition of expected value. All right, so if you do the algebra on this, it turns out that this thing greatly simplifies down that the expected value of a binomial experiment for random variable x is just simply n times p, the number of trials times the probability of success. It's a very simple calculation. And then the variance of our variable then, if you remember, was just the that same summation multiplied by x minus mu, or in this case our expected value quantity squared, multiplied by the probability. All right, so if you kind of look at it, you know, this guy, as we defined it before, is kind of an h of x thing as we look at it. So we're looking at the probability of that particular piece. So, but again, that's kind of a tangent to what we're trying to do here. Okay. All right, you can also come in on this and say that this was the expected value of x squared minus the expected value of x quantity squared would be a way to do it as well. Okay, all right, now if we go through all of this, this formula will simplify down into being n times p times 1 minus p will get us our variance. It's a very simple formula for the variance on this. And then with that, once I have this, I can calculate standard deviation as just being the square root of that guy. And that will be our nomenclature here as well. All right, now let's take a look at what we can do with, you know, kind of a simple word problem. Suppose we're looking at a toll bridge, you know, on this that charges $1 for passenger cars and $2.50 for all other vehicles. Okay, during the day, 60% of all the vehicles at this bridge are cars. Okay, so what we're going to do is we want to find if 25 vehicles cross the bridge, determine the expected toll revenue that could be generated by this. So it's just kind of a simple thing. The hardest part of this whole problem is figuring out what's the toll revenue equation. So this is an h of x equation, and so our toll revenue then is, it's $1 per car. So we're going to define our random variable x, okay, on this, and I didn't write that down. So our x, okay, is going to be the number of cars as opposed to other vehicles. And so that's our random variable definition. Okay, and so if I do that, then I have $1 times x plus $2.50 times the rest of the cars, the non-cars. So if I have x cars, then I have 25 minus x non-cars. And so this would be, you know, n minus x coming in here. All right, oh, there it is. There's where my random variable statements. My random variable of x is the number of cars in a given day. And so if I do the algebra, my equation becomes 62.5 minus 1.5 times x. All right, so if I do the expected value of that function, then we can use our a and b identities, you know, that it looks something kind of like this. A to the x plus b, we said last time, that A times expected value of X plus B on there will get me that expected value of this equation. So if I look at this function that we've derived off of here, we can see that B is 62.5 and A is negative 1.5. All right, so if I plug this in, then that becomes 62.5 is my B minus 1.5 multiplied by this guy, which is the expected value of X. So 0.6 is the probability, N is the number, and if I run this math out, you'll find out the expected total revenue of this is $40. Must be a pretty small bridge, but you get the idea. The exercise is very, very easy to work at on this, okay? And so that's all there is to it. But the big thing to take away from this is that these identities are very, very important to understand all of those and being able to manipulate equations into forms that you can work. Here I was looking for the expected value of some other big function that I may or may not know the value of, but with this identity I can turn it into something that I'm capable of working with that is based off of a calculation that you know how to do, the expected value of X of our revenue. And in this case, because this was binomially distributed on there, you knew that expected value of X was NP. If this had been some other distribution, this process would still work. You just need a different calculation for the expected value of X. And that's where we're going with all of this. All right, so the binomial is the first step in a lot of these on those. We'll make one last note on here that for us that X is going to be binomially distributed, okay, on 25 and 0.6 would be the kind of the definition, the way that you would start to kind of write this. I realize I left that off too. Okay, and so that will get you all of the terms that you need. So this is the beginning of an awesome set of powerful tools, for determining probabilities of events happening. And once I have this, then I can move into statistics a little bit later on those. So all we have to do, so we've got the first one down, we've done the binomial. There will be some others that are coming, things like the hypergeometric and the negative binomial and Poisson and a bunch of others that we're going to cover in subsequent videos. So if you'll stay tuned for those, you can come back and you can look at those particular videos that will be upcoming. But for now, the binomial, hands down, is one of the most powerful ones, just because of that ability to condense a problem criteria from, number of events, in A, and then a, corresponding number of events in not A. So right off the bat, we can almost start doing our pool problems in many cases. So this is a very, very important one to recognize. So make sure that you kind of understand this. If you got any questions, let me know. Leave me some comments down below, and I'll be happy to try to clarify that. And if you're one of my students, just bring it up when we meet, and I'll be happy to elaborate a little bit further. So anyway, hope this kind of showed you kind of how easy it is to set these things up once you understand the basics of a particular experiment. Again, we've got more coming, and we'll continue the videos on those. So leave us some feedback down below. And as always, like or subscribe to our channel, and we will see you next time. Have a great morning. Happy engineering. Thanks.